So in 2018, researchers discovered the Spectre attack, in which an attacker plants malicious predictions in the processor, putting all of your data at risk. This vulnerability was going to haunt systems for years to come.
Never heard of Spectre? Consider yourself lucky, for what it can do gives cybersecurity experts nightmares. Passwords, fingerprint readers, facial recognition. We've built walls to keep your data safe. But MIT researchers just found a crack in these defenses: the processor itself.
Virtually every processor has a predictor which predicts which instruction comes next, and this significantly saves time. When it's incorrect, the processor can simply walk back and undo the effects of the instruction. But what if the prediction is not just wrong? What if it's malicious instead? So that some code executes on the wrong path that reads out a secret and transmits that back to the attacker. These secrets can be anything. They can be your passwords, they can be your keys, or any other information on your computer. Because the secret is accessed in a misprediction, which the processor rolls back, there's virtually no evidence left of accessing that secret.
A typical software vulnerability lives in code, something which can be patched with an update. Spectre doesn't exploit a bug in code. It lives in the silicon, the physical chip inside nearly every laptop, phone, and server on the planet. You can't patch hardware design. Since discovering Spectre and its variants, chip vendors have responded with workarounds based around neutralizing incorrect predictions before using them for any new instruction. But there's a tiny gap in time between those two actions which remained a security vulnerability.
In this work, we explore exploiting that gap, and we call attacks that exploit this gap TONTOU attacks, or time of neutralization to time of use attacks.
One day Daniel came to me and he explained the beautiful idea about how to break the TONTOU window. My first reaction was, this sounds quite clever, but will this actually work?
Good question, because knowing the TONTOU gap exists is one thing, hitting it is another.
Interrupts are these things are essentially happening on the CPU all the time. The CPU has keystrokes, a hard drive, a camera, microphone, all of these things write information into some place in memory and then tell the CPU, okay, I have something for you. And then the CPU then wakes up, looks at it, figures out if it's important, and if it's important, does something with it, and if it's not important, continues with what it was doing.
Interrupts aren't attacker code. They're the routine housekeeping every processor handles constantly. Keystroke, mouse move, network packet arriving.
So we wondered, what if an interrupt happens right into that TONTOU gap? But the problem is, this TONTOU gap is extremely small.
On one hand, the window is super small. On the other hand, whether we can have the precise control of the interrupts is really a big question. So very exciting, but also a lot of uncertainties. We never sure that we can pull it off.
Here's how we did it. We set a timer to create an interrupt at an exact moment in time. And if we carefully choose that timer, it will go off in our TONTOU window. To further increase the probability of this happening, we slow down the processor by wiping the instructions from the cache, forcing the processor to fetch them from further away. And so this increases the size of our TONTOU window by just enough to exploit it. In theory, this should work, but we had to prove it in practice.
Both of us know we put up something really big, but as a researcher, we just want to make sure everything is correct. We just need a few small pieces, which Daniel are very good at doing to pull off the end-to-end attack.
And so we used our timer technique tens of thousands of times to see if we could hit that window. And it worked. 2% of the time.
The thing that is special is that you're able to make it work once. The fact that he was able to succeed 2% of the time, or 2 out of 1,000,000 times, is already quite surprising, because the CPU is supposed to let this happen 0% of the time.
We succeeded in using a timer to create an interrupt right during the TONTOU window, poisoning the predictor after neutralization but before use, causing mispredictions. And we used this to steal what is called an etc shadow file. It's one of the most sensitive files that live in your system, containing hashes of passwords and even those of root or administrator users.
If the etc shadow file can be leaked, the system underneath it isn't secure anymore. Not for one user, for everyone on that machine.
And this doesn't just affect your laptop. If servers in the cloud are vulnerable, then multiple users can become a victim of one attack in one shot.
Your email, your bank, your medical records, they all sit in the cloud on servers you'll never see. One chip on one server affects thousands of users. If the hardware underneath has a flaw, everyone on that server is compromised.
Having achieved our goal, we reached out to AMD to let them know of our techniques. So AMD asked for our code to replicate the attack and to figure out how to mitigate against it.
Thanks to academia, it is possible for the world to actually find out about these problems.
We'll be presenting this research at Black Hat USA and Usenix Security, and we look forward to continuing our research on processor vulnerabilities here at MIT CSAIL.
Spectre was named for a haunting that everyone knew was coming. The chips haven't changed. What counts as a safe window just got a lot narrower.